This is Math 1111, College Algebra, and in this video we will be starting Unit 2, which covers quadratic functions. In this unit we'll look at sections covering radical expressions, complex numbers, polynomial expressions, quadratic equations, quadratic functions, and quadratic inequalities. So we're going to start off with a section on radical expressions. And the way we're going to do this is starting by simplifying square roots. It says to simplify or state that the expression is not a real number. First up, we have the square root of 25, which I'm hoping a lot of you know is 5. The square root of negative 25. Well, before we actually attack that, let's look back at the square root of 25 equals 5. The reason why this is true is because 5 times 5 is 25, or we can get it as 5 squared is 25. So what number times itself gives us a negative 25? There isn't one. So because there isn't one, we state that this is not a real number. And that's because we cannot take any real number and multiply by itself and get a negative 25. Last, we have negative square root of 25, and that's just the square root of 25, but with a negative in front. So this will be negative 5. Sometimes, though, we're looking at square roots that aren't quite so obvious. So on this one, we want to look at the square root of 50. Now in this case, we might be able to figure it out without this method, but this neat little method is going to help us when we do get to the super complicated ones. So we want to find the square root of 50. The way I'm going to do that is by looking at the prime factorization of 50. To do that, I start with 50 at the top, and I find two positive numbers, other than one in the number, that multiply to give me that. So 50 is 25 times 2. And 25 is 5 times 5. So that means 50 is equal to 2 times 5 times 5. Anything that pairs up, in this case I have a pair of 5s, they come together as one outside of the radical, and then anything that doesn't pair up, the 2, stays underneath the radical. So the square root of 50 simplifies to 5 times the square root of 2. The square root of 50x, we're going to see something very similar, because 50x will be 2 times 5 times 5 times x. We still have that pair of 5s, so we get a 5 out front. Under the radical, we still have 2 times x, or 2x. So this simplifies to 5 times the square root of 2x. Next up, we're going to look at the square root of 25x squared y squared. Well, I can do this one without really looking at the tree form of the prime factorization. 25x squared y squared is 5 times 5 times x times y times y. I have a pair of 5s, a pair of x's, and a pair of y's, so they all go out front. There's nothing left under the radical, so this is just our answer, 5xy. Next up, we're looking at the square root of 200 m to the 5th n. So 200 is 10 times 20. 10 is 2 times 5. 20 is 4 times 5. And 4 is 2 times 2. So what I've done is I've taken 200 and broken it down into all of its prime factors. So we looked at 200, and then m to the 5th n will be pretty easy. So 200 m to the 5th n is equal to 2 times 2 times 2. We have 3 factors of 2, and then 5 times 5. Then we have m to the 5th power. So we have m, 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 and then an n. So let's see what pairs up. I have a pair of 2's, I have a pair of 5's, I have a pair of m's, I have another pair of m's, and that looks like all we get for pairs. So what paired up was a 2, a 5, an m, and another m. Left under the radical, because it didn't get paired up, we have a 2, an m, and an n. 2 times 5 is 10, and then m times m is m squared, and we are left under the radical with 2mn. We can also simplify fractions that have square root in them or over them. And we can do this by actually breaking up the square root. There is a rule that says if a and b are real numbers, then the square root of a over b is equal to the square root of a over the square root of b. So instead of looking at this as the square root of 1/25, I'm going to look at it as the square root of 1 over the square root of 25. I know the square root of 1 is 1, and I know the square root of 25 is 5. So our answer is 1/5. We can double check this. If we take 1/5 times 1/5, that's equal to 1/25. So that checks out. The square root of 60 over 3, I'm going to approach it in a similar method as the last one, but kind of backwards. Instead of going from the fraction over the entire thing to split up, I'm going to start with it split up, and I'm going to instead put the radical over the whole thing, 60 over 3. Because 60 divided by 3 is 20. So this is the square root of 20. 20 is 4 times 5, and 4 is 2 times 2. So I have a pair of 2's that did get to come out front, and that leaves the 5 under the radical. So this is 2 times the square root of 5. Now we're going to work on multiplying these. So we just looked at dividing these radical expressions. Something else we can do is multiply them. If a and b are positive numbers, then the square root of a times the square root of b is equal to the square root of a times b. So kind of like how we were able to take the radical over the entire fraction and break it into the numerator and denominator, or vice versa, we can do that with multiplication as well. So in this first case, we're looking at the square root of 12 times 3. That's going to be equal to the square root of 12 times 3, which is the square root of 36, which is 6. We're going to look at this expression here. We have 2 times the square root of 3 times negative 4 times the square root of 51 plus 7 times the square root of 75. So just like we would with other expressions, we can distribute this 2 times the square root of 3 through the parentheses. What that's going to look like is 2 times the square root of 3 times negative 4 times the square root of 51 plus 2 times the square root of 3 times 7 times the square root of 75. Now, some really interesting properties hold when we are adding and multiplying, and one of those is the commutative property of multiplication. And what that says is it doesn't matter what order I multiply things in. So if I look just at this first term, I have 2 times the square root of 3 times negative 4 times the square root of 51. Instead of writing them in that order, I'm going to rewrite this as 2 times negative 4 times the square root of 3 times the square root of 51. And then I'm going to do the same in my second term. So I have 2 times 7 times the square root of 3 times the square root of 75. Well, 2 times -4 is -8. The square root of 3 times the square root of 51 will be the square root of 153. Then we have plus 2 times 7 is 14. And the square root of 3 times the square root of 75 is going to be the square root of 225. Now I need to see if either of these break down so that we can simplify our radicals. So I'm going to do the prime factorization trees. 153. Well, it's not divisible by 2, but it is divisible by 3. It's 3 times 51. 51 also happens to be divisible by 3. It's 3 times 17. 17 is prime, 3 is prime, 3 is prime, so we're at the end of that one. So that means the square root of 153 can be written as, I have a pair of 3's, so I get a 3 out, and then a square root of 17. We'll deal with that in a minute. Then we have 225. Well, 225 is 5 times 45, and 45 is 9 times 5, and then that 9 is 3 times 3. I know that doesn't show up too well, but. So it looks like I have a pair of 3's and a pair of 5's. So this is 3 times 5, which is 15. Oops, sorry, wrote that wrong. The square root of 225 is going to be equal to 3 times 5, which is 15. So now what I'm going to do is, back in my expression here, I'm going to replace the square root of 153 with 3 times the square root of 17. And I'm going to replace the square root of 225 with 15. So I have a -8 times the square root of 153, or sorry, replacing it. 3 times the square root of 17 plus 14 times 15. -8 times 3 times the square root of 17 is a -24 times the square root of 17. And then 14 times 15 is equal to 210. That is as simplified as this gets. We're going to continue multiplying these radical expressions. So next up, we're going to look at 2 the square root of 3 squared. Now, when we see something squared, we have to remember that that means it's multiplied by itself. So we have a 2 plus the square root of 3 times 2 plus the square root of 3. And I'm going to FOIL this, or you can think of it as distributing it. My 2 gets distributed to the 2 and the square root of 3. So it's going to be 4 plus 2 times the square root of 3. Then I need to distribute my square root of 3 through, and I get the square root of 3 times 2, which is a 2 times the square root of 3. And then the square root of 3 times the square root of 3 is the square root of 9. So that's 4 plus 2 times the square root of 3 plus another 2 times the square root of 3 gives us 4 square roots of 3. And the square root of 9 is 3. If I combine my 4 and my 3, I get 7 plus 4 times the square root of 3. Next up, I'm looking at 2 plus the square root of 3 times 2 minus the square root of 3. I'm going to distribute or FOIL like I did in the last one. 2 times 2 is 4. 2 times a negative square root of 3 is a negative 2 times the square root of 3. I have a positive square root of 3 times 2, so plus 2 times the square root of 3. And then a square root of 3 times a negative square root of 3 is a negative square root of 9. So it's going to be 4. My negative 2 square root of 3 and my positive 2 square root of 3 cancel out. Minus the square root of 9 is 3, which leaves me with just 1. We're going to work on adding and subtracting together these radical expressions, because sometimes it seems easy, sometimes it doesn't look quite so obvious. So what needs to be true when we're combining radical expressions is that they have to be the same type of radical. So in this case, they're both square roots, or I guess all four of them are square roots. If there was a different index, so if we saw a number in here like a 3 or a 4, they'd have to have the same index. But they also have to have the same radicand, the same thing underneath the radical symbol. So they both need to have a square root of 7, or they both need to have a square root of 15 in order for us to combine them. So in this case, we have a 4 square root of 15 minus a square root of 15. But what that really means is minus 1 square root of 15. So if I have 4 square roots of 15 minus 1 square root of 15, that leaves us with 3 square roots of 15. And then we have a negative 3 square root of 7 plus 7 root of 7, and that's a positive 4 square root of 7. That's how this simplifies. In the next one, we're looking at 2 times the square root of 3 minus 3 times the square root of 243 plus the square root of 75. Now it looks like we can't do anything with this because none of them appear to be like terms. But what we need to check is if any of these simplify, any of these radicals. So the square root of 3 can't be simplified, but maybe 243 can. So 243 is 3 times 81. 81 is 9 times 9. And each of the 9s are 3 times 3. So that means the square root of 243 is equal to, I have 1 pair of 3s, I have 2 pairs of 3s. So I get 3 times 3, which is 9, with an extra 3 left over that stays under the radical. Then I have the square root of 75, and 75 is 25 times 3, and 25 is 5 times 5. So that means the square root of 75 is 5 times the square root of 3. And once we have those radicals simplified, we'll see that we are going to be able to combine some like terms. So we have 2 times the square root of 3 minus 3 times the square root of 243 is 9 times the square root of 3, plus the square root of 75 is 5 times the square root of 3. So we have 2 square roots of 3 minus 27 square roots of 3 plus 5 square roots of 3. So 2 of them minus 27 of them is negative 25 of them, plus 5 leaves us with a negative 20 square roots of 3. Now there are some rules in math that people just kind of know because we're just taught this is the way you do it, so that's the way we do it. One of those things is rationalizing denominators. We don't want to leave any radicals in a denominator. So if you have a square root in a denominator, you're going to want to get it out. So in this first case, we have 2 divided by the square root of 7. If you just have a square root sitting by itself, you're going to want to multiply the numerator and denominator by that square root. So I'm going to multiply the numerator and denominator by the square root of 7. So in my numerator, I have 2 times the square root of 7. And in my denominator, the square root of 7 times the square root of 7 is the square root of 49, which is just 7. So this answer, 2 times the square root of 7 divided by 7, is preferred because we don't have a radical in the denominator anymore. In the second one, we're looking at the square root of 3/5. Like we did earlier, we can break up the radical into the numerator and the denominator. So the square root of 3 over the square root of 5. Just like I did in the last one, I'm going to multiply by that square root that's in the denominator to the numerator and the denominator. The square root of 3 times the square root of 5 is the square root of 15. And the square root of 5 times the square root of 5 is the square root of 25, which is just 5. We cannot simplify this fraction. That 15 is under a radical. We can't simplify it unless the denominator is under a radical as well. So that's it. We're done. But we don't always have a radical sitting by itself in a denominator. Sometimes we have a radical plus a whole number. So in both of these examples, we have 2 plus the square root of 7 in the denominator. And you might be wondering, well, how do I get it out of there? Do I just multiply by the square root of 7? Well, no, that's not going to work. So I want to take us back a couple of examples. We multiplied 2 plus the square root of 3 times 2 minus the square root of 3, and we just got a whole number. So we're going to try that here. What we're going to need is the idea of a conjugate. So a conjugate will be if you have a plus the square root of b, turning it into a minus square root of b, and vice versa. So if right now I have 2 plus the square root of 7 in my denominator, I'm going to multiply by the conjugate of that in my numerator and denominator. So I'm just changing the sign on the radical term. It was 2 plus the square root of 7. Now it's going to be 2 minus the square root of 7. But if I multiply the denominator by that, I also have to multiply the numerator by that. So in my numerator, I have 1 times 2 minus the square root of 7, which is just 2 minus the square root of 7. In my denominator, I'm going to have to FOIL this out because it's 2 plus the square root of 7 multiplied by 2 minus the square root of 7. 2 times 2 is 4. My outside terms, I get minus 2 times the square root of 7. My inside terms, I get plus 2 times the square root of 7. And then we get plus the square root of 7 times minus the square root of 7, which is just going to give us a minus 7. Those middle terms cancel out, the minus 2 square root of 7 and the plus 2 square root of 7. So what we're left with is the 2 minus the square root of 7 in our numerator and 4 minus 7 in our denominator, which is 2 minus the square root of 7 over a negative 3. That's a perfectly acceptable answer. If it makes you uncomfortable having a negative in the denominator, you can move it to the numerator. Just make sure if you do so that it gets distributed to the numerator. So that way it would be negative 2 plus the square root of 7 over a positive 3. This answer is okay, this answer is okay, this answer is okay. They are all perfectly equal and perfectly wonderful. We're going to attempt the same strategy with this next one. We have 1 minus the square root of 5 over 2 plus the square root of 7. We want to make sure we don't have a square root in the denominator anymore. So we're going to multiply by the conjugate, 2 minus the square root of 7. And if we multiply it in our denominator, we also have to multiply it in our numerator. This time I'm going to have to FOIL both my numerator and denominator. So I'm going to have a lot of terms floating around. So 1 times 2 is 2. 1 times the negative square root of 7 is a negative square root of 7. Negative square root of 5 times 2 is a negative 2 times the square root of 5. And then negative square root of 5 times a negative square root of 7 is a positive square root of 5. All over, we already did the multiplication, 2 plus the square root of 7 times 2 minus the square root of 7. So I'm just going to jump to the fact that that's negative 3. It doesn't look like I have any like terms in my numerator. This one's a square root of 7, this one's a square root of 5, this one's a square root of 35. We should check to see if that square root of 35 simplifies at all though, because if it does, then it might be able to combine with one of our other terms. The problem with that is 35 is just 5 times 7. Nothing pairs up to come out of the radical. So it doesn't simplify. This is it. We can't do anything with that. However, just like in the last problem, if you're uncomfortable having a -3 in the denominator, you can move the negative to the numerator. Just be sure that it gets distributed. So we have negative 2 minus the square root of 7 minus 2 times the square root of 5 plus square root of 35 all over a positive 3, which if you distribute through is -2 plus the square root of 7 plus 2 times the square root of 5 minus the square root of 35 all over a positive 3. Any of these three are perfectly wonderful answers.